High-voltage direct current HVDC is a modern transmission technology designed to move electric power over long distances using direct current DC instead of the more common alternating current AC. Unlike AC systems, which oscillate and experience reactive losses over distance, HVDC ensures minimal energy dissipation, precise control of power flow, and the ability to interconnect asynchronous grids. This makes it especially valuable for linking isolated generation sites, integrating renewable energy like offshore wind farms, and supporting cross-border energy trade. HVDC also requires less land and has narrower right-of-way requirements, making it ideal for congested or challenging terrains. The Monopolar HVDC system is the simplest and most cost-effective configuration of HVDC transmission. It employs a single high-voltage conductor typically operating at a negative polarity and uses the ground, C, or sometimes a dedicated metallic line as the return path for current. At each end of the transmission corridor, converter stations perform AC to DC conversion rectification and DC to AC conversion inversion, enabling seamless integration into conventional grids. One of its key advantages is reduced infrastructure cost, as only one conductor is needed for transmission. However, reliance on earth return introduces several challenges. Ground currents can lead to corrosion of underground metallic structures such as pipelines, interfere with communication networks, and affect the surrounding environment due to stray currents. Monopolar systems are often deployed in remote areas or as submarine links between islands and mainland grids. In modern practice, metallic return conductors are increasingly used to minimize environmental risks, despite the added cost and complexity. While fault tolerance is limited since any issue in the lone conductor interrupts transmission, the simplicity and economic viability of monopolar HVDC make it an appealing choice for low to moderate power transfers over extended distances. A monopolar HVDC system is a fundamental transmission configuration that employs a single high-voltage conductor, typically operating at negative polarity, with its return path flowing through the earth, C, or where environmental constraints demand a metallic return conductor. The converter stations positioned at each terminal generally utilize 6-pulse or 12-pulse converters to manage the rectification and inversion processes. For systems relying on earth return, dedicated electrode lines are installed, connecting to ground electrodes placed at considerable distances from converter stations, typically ranging from 15 to 55 kilometers, to minimize interference and ensure safe current dispersion. In cases where environmental preservation is paramount, a second conductor is introduced as a metallic return at medium voltage to eliminate direct ground current.